Log on, tune in, find out. Another good idea from Cambridge.
Should we go ahead and start? Okay.
Not yet.
Wait, 30 seconds.
We have a problem. There is no choice. Very little. There is some here, but there's some. No, there is some.
Is enough? Or?
Yeah, is it there? Okay.
Go ahead.
Okay. It's my great pleasure to welcome Corrado De Concini from Rome, who will tell us about quotients of symmetric varieties.
Yeah. So I thank you very much, organizers, for inviting me here and also to ask me to give this talk. And when I came here, I discovered that all the talks I wanted to give were already given by co-authors or collaborators, because one was given by David Hernandez and the other is going to be given by Prof. So I had to find a talk that, on the other hand, was the most pertinent to our meeting, because it's really a talk about this algebraic geometry of Lie theory. Okay, so this talk is about a paper which I think appeared in the Moscow Mathematical Journal in the last, I think, issue 3 or 4 of 2008, and it is by myself, Cannon and Maffei. And I must say that this talk is going to be, I mean, the result of this talk, I find them nice, but maybe slightly pointless. So let me start saying what we were aiming at. So let's take a field K algebraically closed, characteristic of K not 2, but in order to avoid, non-reduced group schemes, maybe you can assume today, only today, I mean, the results are that K, the characteristic is big. Okay. And let's take G be a simply connected semi-simple group over K, and sigma an order 2 automorphism. And then we are going to consider the fixed points, which we call H, and then we are going to take a group which is in the between the K between H and this normalizer. So again, the quotient of NGH modulo H is finite, so there are not so many. But again, for today, in order to avoid discussion of isogenies and things like that, I will assume that in fact K is equal to this. So today K. And then the aim of the talk is to try to study more or less the action of H on some completion, and we have to say what it is, completion of G mod K. Okay. So this problem, which I say maybe is a bit futile, has a long history. First of all, there is an infinitesimal version of course, among all completion. So let me say what completion means. But completion maybe is the wrong word. I would say embedding. So embedding is Y is embedding, is a G variety, together with a point, and such that the map from G to Y sending G to G mod P embeds G mod K as a dense open set. Embeds G mod K as a dense open set. So this means that the stabilizer of P is exactly K, and the orbit of P is a dense open set inside this. This thing could be, very first example is what is Y equal to G mod K. And of course you take as a point the image of the identity. Okay, so in this case, in fact, in a slightly different case, the study of the action of H on G mod K was, I think this problem dates to constant rallies, I think 1971, and they studied the infinitesimal version. So namely and I think they also work in characteristic P, in characteristic 0, sorry. So the GH equal Lie of H. Then sigma gives a involution of the Lie algebra. And so the Lie algebra splits as the 1 eigenvalue and minus 1 eigenvalue. And of course, P is stable under a joint action by H. So H acts on P. And they studied this action, and they proved a lot of very nice properties, which I will not tell you because I will tell you in the more group case. Namely, that the quotient is smooth, is obtained by a certain Cartan subalgebra modulo a Weil group, and so on. And that the quotient is equisingular, and there are, for any, if you fix the invariance, there are only finitely many orbits having this invariance, and so on. So I will not state it because I'm going to state it in a minute in the group case. So I think that Richardson in 1991, I think, if I remember, this I'm not sure, he studied the G mod K case, so really the group case, and this is studying characteristic not 2. And he proved the various facts which I want to state here. So first of all, but in order to state them, I have first to introduce some notation. So what we have to introduce in this situation is a maximal torus and a Weil group. So this is, of course, very classical theory of symmetric spaces. What we take S in G, a torus, which is maximal with respect to the following property, that if S is in S, sigma of S equals S inverse. Okay. So let me write on that board. And then, of course, if we have such a torus S, we can complete S to a maximal torus in G. And then when you complete it to a maximal torus in G, you have that automatically T is preserved by sigma. So sigma T is equal to T. And sigma induces a map on the character group. So sigma gives a map from xt to itself. And so it preserves the root system. So sigma of phi is the root system, is equal to phi. And then you can define in XS a bunch of vectors. So these are all the alphas, such that alpha is non-zero, and that exists alpha tilde in phi, such that alpha tilde restricted to S equals alpha. So sorry. So this is a finite set of vectors, non-zero, and one can show that this is again a root system. So again root system. possibly non-reduced root system. So there could be roots which can be divided by 2. So we have this the root system which is called the restricted root system. This root system has a Y group, WR, which is in fact the normalizer in H of S modulo the centralizer in H of S. Okay. So now I can state what Richardson proved. So we take, and I want to keep it here. So we take S and we map it down to G mod K. The image is just the set of order 2 points essentially, a little bit more, but okay, so we get the image, we call it S tilde. And then by the fact that the Y group is of this type, we clearly see that W acts on S. So W acts on S tilde. And he proves, first of all, if you take the functions invariants under H, and you restrict to functions on S tilde, you end up in the Y group. We saw these things, for example, in Laurent, he said something that is more or less. It goes to the functions invariant under W, and this is an isomorphism. So we would say that the categorical quotient is equal to S tilde mod W. R. Okay. Secondly, so then we consider the quotient morphism from G mod K to G mod K mod H. So this is just the spectrum of the ring of invariants. Okay, so there's not, you should not be scared by this double Z. Then phi inverse of any point is a finite number of orbits. 3 pi is equidimensional, meaning that each fiber has the same dimension, which is of course the difference in dimension. And 4, an orbit O in G mod K under an H orbit is closed if and only if O intersection S tilde is non-empty. Okay. So, for reasons that I will sketch now, what we want to do is to generalize this to more complicated embeddings. So the reasons were the following: that which were not serious reasons. So among these embeddings, there is a remarkable embedding which is called the wonderful embedding, and it's wonderful because, as we shall see in 5 minutes, it has a lot of nice properties. Now, and among the examples, there is of course the example in which G is H times H, sigma of H1, H2 equals H2, H1, and then G mod K is essentially the adjoint group. Okay. So for this embedding, this very wonderful embedding, which exists in general, is called the wonderful group compactification because of the adjoint group. And this is a G times G variety. And of course you can H times H variety. And you can restrict the action to the fixed points, like we are doing now. So to the diagonal, H diagonal. And you may ask, so this is some kind of completion of the adjoint action of a group on itself. So you, for reasons which I don't want to say, Lustig studied this, and showed, and for example, he classified orbits. And the classification is very complicated, but still tame, you know, in the sense that you have a number of continuous parameters, a number of discrete parameters. I mean, it would take the whole hour to describe all the parameters. So you could expect that the orbit, the study of orbits here could have similar properties, but unfortunately this is not at all true. For example, as soon as H is not of type A1 and A2, there are orbits whose closure contains infinitely many orbits. These orbits whose closure contains infinitely many orbits. And there are other pathologies which this I think is a result by He and independently Esposito. So I could say that the only real motivation to study this problem is that since this compatibility is called wonderful and this situation is sort of ugly, my idea was, well, maybe we could use some trick to restore wonderfulness. And the trick is to use invariant theory. So instead of working with all orbits, we take only semi-stable orbits, and then maybe the situation. So why I did, and we did, not many more. But let me tell you that A appears to have some results using these things. And also I should mention that A and star have studied similar problems of studying the action of H on semi-stable points in the group case, but under twisted actions. So sort of intersecting, but not one containing the other. Okay, so now that I explained the plan of what we wanted to do, which is try to generalize this, I have to tell you what are the embeddings we want to work with, and I also have to tell you what are our generalization. Okay. So this. So now I will write some words which have no meaning, and then I will give meaning to the words. Okay. Okay. So I will write some words which have no meaning. And the words that have no meaning are these. So we are going to work with complete, but projective, smooth, and up to now they have meaning, and then toroidal, this is the less meaning, embeddings, and of course since we are working with projective embedding, in order to do quotient, we need a polarization. So we need to choose an equivariant line bundle. And so we need, we are with polarization. Is given by what is called a spherical line bundle. Okay. So this again a word which probably doesn't make any sense to you. So now the next task of the talk is to explain these words. Okay. Okay. So in order to explain, so this is easy to explain. This is more complicated, but on the other hand, the explanation I will give will also tell you how all these things are constructed. Since I think that they are going to be useful eventually, maybe this is the most interesting part. although it's an old construction we did with Procesi maybe 20 years ago. So in order to say what is a toroidal embedding, we need to say what is this famous wonderful compactification. So this is very easy. So we take G degli algebra, okay, and then we have that the Lie algebra of H is of course a subspace, so it's a point in the Grassmannian of G. Okay. So now, of course, the G acts on the Lie algebra by a joint action, so it acts also on the Grassmannian. So G acts on the Grassmannian. Okay. So what, and the stabilizer of H is exactly K. This is why I chose K. Why I took the characteristic to be slightly large. So the map from G to GH factors to G mod K. Okay. So in order to get an embedding, what you do, you close it down in the Grassmannian, and you get an embedding. So you define X to be GH closed. And of course, the point is just H. So since by definition an embedding is a pointed variety, as a point you take H. So this is certainly an embedding. There is absolute no reason why this embedding should be, for example, be smooth. It is certainly projective because the Grassmannian is projective. But, so this is a closed set in a projective variety is projective, but there is no reason why it's smooth. And this is the fact that it's wonderful. So let me state, where do I state it? There. Now that I think moves like this. No, this moves. I state this. Why is wonderful? Okay. 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 Okay, so X is wonderful because X is smooth. Okay. B, every orbit closure in X is smooth. C, X minus the orbit GH is a union, is a divisor with L equal dimension of S irreducible components. Okay, each smooth, each orbit closure. And smooth, and D, if you take any orbit, O, G orbit, and you take di1, dis, the divisor containing O, then di1 transversal intersect, these are irreducible components with smooth transversal intersection. Di1, dis is exactly O closure. And, well, the last wonderful property is that all of them intersect in the unique closed orbit. So, D, E, intersection I from 1 to L, di is unique closed orbit. Okay, so this theorem was proven in characteristic 0 by I think Procesi and myself, and in characteristic different from 2 by Springer and myself. In fact, there is a better version which is really a scheme over Z with two inverted. So it's really a flat scheme over, but this we don't care. Okay, so we have this variety in which really the orbits look like the, so for a rank 2 space in which the orbits like two lines in, of course each of these is made it fat by the action of G, but locally they look like the intersection of, or if it's three-dimensional, like three hyperplanes, the three coordinate hyperplanes. And the closed orbit is this point. Okay. So this is kind of the smallest toroidal variety, toroidal embedding. Now let me come to the definition of toroidal embedding. So definition. Y is toroidal if Y lies over X. Namely, there is a G equivariant map from Y to X sending the point to this H. Of course, this map, as soon as it exists, is unique. So these embeddings are really a partially ordered set. And all the elements larger than X are called toroidal. Example, G mod K is toroidal, because G mod K, the inclusion of the open orbit, is toroidal. Okay. So now we have that we have made reason to this toroidal, and then we have projected. We know smooth we have, so we have this. Because we know very little about this toroidal. Now I'm going to explain you how to construct them all. Very easy. Because they are completely determined by a toric variety, as we shall see. While the others are determined by toric variety plus some extra data. Okay, so these are called toroidal, and before I tell you how toroidal look, let me tell you what polarization is. And this is also easy. So this I will write it here. We have, of course, G mod H maps to G mod K, and this maps to Y. So we have this map, gamma, and L is spherical. Spherical. If gamma star of L is trivial. I don't say anything about linearization because all line bundles are canonically G-linearized. This is why I took the simply connected group. And let me say that unless the involution, the symmetric spaces are not all, but a special kind of Hermitian symmetric space, if you take any line bundle and you maybe take a small power, in fact I think even 2, it's immediately spherical. If the variety is an Hermitian symmetric space of a certain kind, you have this form, they span a sublattice of rank 1 less than the rank of the Picard group inside. So they are really, almost all of them are spherical. Okay. So it's not a very big restriction. Okay. Okay, so now I have to construct all the toroidal ones. Okay, so how do I do? How do I do? Well, this is an idea which we had with Claudio already a long time ago. And that can be expanded to characteristic P immediately because it involves toric varieties which are characteristic free, so you don't have to worry too much. And this construction is sort of stupid construction, but not completely stupid. So let's start with X. So X has these divisors, D1, DL. You can take the line bundle DLI, which is the line bundle associated with the invertible sheaf of DI. Okay, I write it. some kind of not precise notation. Now, of course, di is an effective divisor in this sheaf, so it has an equation. Okay. So there is Si belonging to gamma xli g, so an invariant section because this is closure of an orbit, such that Si defines di. So the zeros of Si are di. Of course, Si is not completely well defined. It is defined up to a constant, but non-zero constant. That doesn't matter. Okay, so we take vector bundle L1 direct sum LL, and we have section. We have a section S1 SL. Okay. So if we remove from the vector bundle all the points where any of this is 0, we get a principal GM to the L bundle because we remove all the hyperplanes. So we take V star, which is L1 star. This is very badly written, but it means that all coordinates in all Li are different from 0. Okay? So I should write all the points in L1 such that no component is 0. So it's the set of V1 VL such that Vi is different from 0 for each I. Okay? So this is clearly stable under G. This is, of course, a generalized bundle. Stable under G, and it is a principal GM to the L bundle because we have removed the hyperplane. So this is a principal GM to the L bundle. Okay? But once we have a principal GM to the L bundle, for any GM to the L variety, for any variety in which on which GM to the L acts, we can produce a new variety. So let's call this principal GM L bundle B. Now B looks like Bolenzano tau. Okay. So we have this principal G to the L bundle, and we have this tau. Okay. Now we take any Z variety on which GM to the L acts, and we can form tau times GM to the L Z. So this bundle with fiber Z. So for example, if we take tau times GM to the L AL, so just the stupid action of the multiplicative group to the L on A to the L, what we get back? We get back B. We have put back the, we get B. Okay. So we have in this way we have an ample zoo of varieties on which G acts, which we produce from this tau. Of course, we have to choose one of these. So let's choose in this Z a smooth, proper over AL GM to the L embedding. Okay. So a toric variety which is smooth, projective, which is projective over AL. For example, we could blow up the origin in AL, or blow up some coordinate subspace, or do things, or blow up twice. We have infinite, but they are all classified by combinatorial data. You should remember that all these things you start with the quadrant in Rn, which is associated to AL, and then you just decompose the quadrant in cones which are spanned by integer vectors, and such that any cone is spanned by a basis. So the rays of the cone, each cone is simplicial and spanned by a basis of the lattice t to the n. This is to ensure that smoothness. And projectivity is slightly more difficult, but properness just that covers this. So this is by all theory of Mumford, Knudsen, and on I, it's completely determined by completely combinatorial set of data. Just, I don't know, for example, in AL you want to blow up, in A2 you want to blow up the origin, you take the bisectant. Then you have two fixed points. You take another bisectant, you blow up one of the fixed points, and so on. Okay, so it's something that you control. Okay, now I am almost through. I'm almost through, and then I'm almost through. So I take such a z. So I take tau times gm to the L z. This maps to v, because this is tau times gm to the L AL. And so you have a map from z to the L, you have this. We have x here. And now we remember we have the section. This map is equivariant because the action is on the left of tau. So this is a G variety and this map is equivariant. This section is invariant section because this has a very invariant section. So and what do? We do the Cartesian product and we get y. And we remark that in fact if we take G mod H here, these are exactly the points for which the section lies in tau, because it's never 0. So this leads to this upstairs. And so y is a G mod K, sorry. So this is y, Cartesian product is G mod K embedding. And then what you prove, theorem, every smooth, projective, toroidal G mod K embedding is one of the y's. So every smooth toroidal projective embedding is obtained in this way. So the classification of this smooth toroidal projective embedding is just the classification of the compositions of the positive quadrant into nice cones, each spanned by a basis of z to the n, which cover this, and which a slight extra convexity property due to the projectivity. If I would remove any of these sentences, for example, if I would remove smooth, I would not care about being spanned by a basis. If I would projective, I would remove the fact that they cover and this extra convexity property. So, for example, the G mod H, G mod K is toroidal, just corresponds to the origin. Just the embedding, this is iodic composition. You just take. Okay? So this is the classification. So now we can state a theorem. So we took about all the lectures to introduce all the data, and now we are ready to say what, at least at the beginning, what we prove. Okay, so now you know what is a toroidal, smooth, projective embedding, what is a spherical line band, and now I can state it. Okay. So the first theorem, so what we did was very stupid. We had Richardson results. So what is the first result? This result. Okay. So what is our theorem? let Y smooth projective toroidal embedding of G mod K. L ample spherical line bundle on Y. Of course, I don't have to say that this linearization because there is one canonical linearization. Consider the H0, but you don't even need ample, YL, 2 H0, set Ys equal S tilde closure in Y. So the closure of the torus which was contained in G mod K. Ys, L restricted to Ys. So this is really the analog of this torus S tilde. So we add to the torus whatever points it reaches in the boundary. Okay? So this is just a restriction map. Pass it to invariance, then, so this restriction, then R gives isomorphism between H0, Y, L, H, and H0, Ys, L, Ys, W. Okay? So this is isomorphism. So let me say 2 words about the proof of this theorem. The proof of this theorem is essentially trivial. And once you know exactly how this map behaves and how this section decomposes into irreducible modules. And in characteristic theory, this was known for a long time. It was proven, I think, by Buffet and Briand around 1990. Unfortunately, in characteristic P, one really has to work a little bit. And essentially, one has to prove that this guy has a nice filtration, has what is called a good filtration. So I have to prove, to show H0 YL has good filtration. So in fact, for the wonderful variety, this fact has been proven by Springer and myself, but in general, maybe because nobody ever cared, it was not proven. It turns out not to be completely obvious. I mean, because the filtration, for the wonderful variety, there is a canonical filtration and should be good. But in this case, you have to work a little bit. So even in this case of X, it was, for me, the hardest intrusion in characteristic P. I had to use tilting modules, all these things that I don't understand to find a proof. So it was not completely stupid. I mean, and here it's sort of the same kind. Okay, once you have this, of course, then you are done. Because if once you have this, you have that you sum over all powers of L. So you take the projective coordinate ring. So you have isomorphism between direct sum H over N bigger than or equal 0, H0, Y L to the N, H, and H0, Ys, L restricted to Ys, WR, okay? To the N, sorry. Yeah, and direct sum. So this is nothing else than the projective coordinate ring under L of Y, and this is the projective coordinate ring of Ys. So this is, of course, implies that Y mod H is isomorphic to Ys mod WR. So, and it also implies something very strange. This thing depends on L because it depends on the polarization, but this thing is just the usual topological quotient. So a corollary is that Y LH is independent from L, which maybe is not such a good news because nowadays there are a lot of emphasis on wall crossings, stabilities, and so on, but there is no wall crossing, no stability. They're all the same in this case. So it's a completely idiotic. So from the point of view of this fact, the wonderfulness is restored. Now we have to show this. Okay, so now we have to show this, and I have not so much time. Okay, so let me. This is not. I mean, the second part, the analog of 2, 3, and 4, is really surprising to me. Maybe not to you. You will explain me, but I could not really understand what happens. So now what we want to study is the quotient. To study is the quotient pi from y to y mod h. Of course, I can write like this because it doesn't depend on L. But of course, this doesn't make any sense because we know by invariant theory what we know, that we cannot, this is not defined. It's defined only on what they are called semi-stable points. So pi is only defined on YSS, namely the points y in Y, such that there exists an n and an s in H0 y L to the n H with S of y different from 0. Because you see, this is a projective animal, and so a projective animal must have at least one coordinate different from 0. There is no point in projective space with all coordinates equal to 0. So you need this. So now the problem is that in order to study this map, we better first identify this YSS. So I have to understand, to see what is YSS. Okay. So since I was very slow, as usual, and I don't want to stop processing, I will jump a part that I had prepared on explaining how these orbits on this Y fiber onto varieties of parabolic subgroups. And I will just, by the strength that I have being the lecturer, tell you that this happens. Okay. So, I mean, unfortunately, because otherwise I cannot really say anything. Okay. So, fact, see, this is an old fact on the wonderful compactification X. So the fact is this: if you take an orbit O, a G orbit in X, you know that we have all these orbits which are intersection of divisors and so on. Then to O you associate a parabolic subgroup PO and a fibration PO. Okay, just projection. And this projection has the following very nice property, that first of all the Levy factor is sigma stable, and the fiber on PO, so remember this is a variety of parabolics, so it contains PO, is just L bar O modulo L bar O sigma, where L bar O is a joint group. Okay, so we know this. The philosophy of this is what? Is that we have a G mod P, and upstairs we have another symmetric space, which we could study with the same methods. So we could do invariant theory on this. unless as soon as we have a control of how are the semi-stable points. Okay. So how could we reduce to this? Well, the best thing would be that the semi-stable points are just the pre-image of a single orbit, because then the whole structure of orbits is determined by the action of L bar sigma on the symmetric space. Okay, so let me study now YSS. Okay, now let's study YSS, and we studied YSSO, which is YSS intersection O. But O is G orbit in Y. So first of all, G orbit in Y maps to a G orbit in X, because if you take a G orbit, the projection. So we have the map from Y to X. This maps O to O prime. And O prime maps to G mod PO. Okay? And the fiber now is not this, but is some L tilde modulo L tilde sigma. So it's some piece of the Levy factor, not anymore the full semi-simple Levy factor, but also some reductive part, which I don't want to say, but it can be read from these combinatorics. Okay. Okay, now take YSSO, and then we have this proposition. H in G mod PO as a unique, open, affine orbit AO. Okay. So this unique open affine orbit is what? Is the complement of the divisor defined by a H invariant equation. And you can imagine that by moving a little bit, you can put this equation back in this section. So from this you deduce fact YSSO is, so let me call this projection PO equals PO inverse of A. So the closed points, the semi-stable points in each orbit are just the preimages of this affine variety. But this is a affine morphism, so they are affine. They are affine. They are affine. And then on them, the quotient is just the usual affine quotient. So you have affine with an H action, and the quotient is the usual affine quotient. So what we have? We have this Y, and this YSS is a union of YSSO, each over all orbits, of all G orbit, or G orbit, and each of these fellow is a affine variety. Okay, so this is quite, to me, surprising. In fact, if you do non-toroidal examples, I will tell you one. Immediately you see this is absolutely not true. You need toroidal. IOSS affine. Okay, and then when you take YSS mod H, this is just the union of YSSO mod H, but this is the usual affine quotient. So in particular, you deduce the following facts. First of all, two. For any P in y mod h, pi inverse of p is a finite number of orbits. So we have generalized 2, and the reason is that more or less you look inside each of them. 3, if B is H orbit in YSSO, then its closure in YSS all lies in O. So the closure relations of these orbits of semi-stable point, they really behave orbit by orbit. They don't interact one with the other. You have really cut the variety in pieces, and each piece behaves very well by itself. Okay. 4. So what we have? Pi is equidimensional, and 5 B in YSS H orbit is closed if and only if B intersect YS, which is the last. So we by some miraculous to me, the first part about the Y group I was more or less expecting. But with some miraculous and not very enlightening proof, we have seen that this result of Richardson expands to all these things. And in fact, it's a very amazing fact that you can reprove all the results of Richardson from this. So let me explain you why. So I will not explain you why. I will just state. So the fact is that, you see, we have seen that this quotient behaves orbit by orbit. So you arrive in a G orbit, you find a point in a G orbit, and to see how the quotient behaves, you have to see in the G orbit. So this means that this quotient makes sense also if you remove a few G orbits. So if you remove them all, except the open orbit, you can study this directly. So you get back the result of Richardson. So I'm a bit cheating but that is part of it. So the fact that the quotient respects G orbits implies can do also same results for any G stable open in Y, in particular for G mod K. Okay. The second thing, and then I will quit, so don't worry. The second thing that you may wonder is why I have to bother you with all this toroidal and all this. I mean, I spend almost all my talk saying what is the assumption. So first of all, because I like this toroidal and I think people should study it. And in fact, Springer also studied these orbits, and it seems that for character shifts reason, one is forced to use this toroidal. I mean, you cannot use only X. And but the other reason is that the results are just simply not true for non-toroidal. For example, so I will end up with some very simple example, namely the following. You take y equals P8, so 8-dimensional projective space, which is P of 3 by 3 matrices. So this is the compactification of PGL 3. Okay. And you take L to be O1. It's spherical, but this is not toroidal, this compactification. And you take the following matrix. So now, if you take the H0 y L to the n, this is Ericsson, n, this G, where G acts by conjugation, where this is a polynomial ring in 3 variables, generated by the trace, the second coefficient of the symmetric polynomial, and the determinant. Okay. So this is just k of t, d, and I don't know, second coefficient, t, d, l, p. Okay. Okay. So now, if you take the following matrix, 0, 0, 1, 0, 0, 0, 0, 1. The trace of this matrix is certainly non-zero, and this is a semi-stable point. Semi-stable. Okay. On the other hand, if you put t here, and this has rank 2, you degenerate this to the matrix. So if you put t here and you send t to 0, you degenerate to this matrix, which is also semi-stable, has the same invariance, but it's rank 1. So we have gone out from one orbit and gone to another orbit. Also, this thing, I say, it doesn't map to the open orbit, because what is the projection from rank 2 matrices to a G mod P? It's just the map. So if you take rank 2 matrices, D2, you have to map it to P2 times P2, where one P2 is the line which is the kernel, and the other one component is the kernel, and the other component is the image. It's rank 2, so the kernel is one dimension, the image is one dimension. Okay. So what is the open orbit? Are those pairs line hyperplane in 3 space which don't meet? But you see, the kernel of this matrix intersect the image, because the kernel of this matrix is this, no, but the image contains this. So this map is not in the open orbit. So this matrix A does not map in open orbit. And in fact, you can easily cook also that for this example, you can cook another strange thing. That although I said that the quotient makes sense also for open embeddings, of course, for open embeddings, you could do something else. You would restrict the line bundle, and then you take the invariance. And you may ask, do I get the same quotient? The answer is no, because in one, this will be a semi-stable point, in the other, it will be not. So you have to be, when you do invariant theory, you have to be careful on what you say. So the good quotients we do of non-compact things are just the image of non-compact things inside the compact quotient. If you want to do it directly for non-compact things, you get different. I think I stole almost 5 minutes, so I should quit.